Good afternoon and welcome to our lecture on the normal distribution. So last time we learned the first two orders of business that we want to accomplish when learning the normal distribution, and that is, given a value in the distribution, we can find areas or probabilities associated with seeing that value, and then the reverse, given a probability, we can come back out with a value, and we did that in the form of percentiles. The third order of business is to learn about z-scores. The standardization formula for a normal random variable, that is y that's distributed as a normal with some mean mu and standard deviation sigma, is z equals y minus mu divided by sigma. Now the y in there is the observation you want to standardize, and of course the mu and the sigma are the mean and the standard deviation of the normal distribution that the observation came from. Now, after you standardize your normal random variable, you come out with this whole set of z-scores if you standardize every value in the distribution, and that variable has a very special distribution, the normal distribution that has the mean mu of 0 and a standard deviation sigma of 1. And that special standard normal distribution that's centered at 0 and has standard deviation 1 is called the standard normal distribution. A z-score has a special interpretation. It is the number of standard deviations an observation is above or below the mean. A positive z-score means that the observation is that many standard deviations above the mean, and a negative z-score is the number of standard deviations the observation is below the mean. For example, we're going to find the z-score for a herring with length 60 millimeters. Now, if you recall from last time, the herring length distribution was a normal random variable centered with mean at 54 and standard deviation of 4.5. So that's the example we've been working with all through the set of lecture notes. So we want to standardize an observation. So we have our formula, z equals y minus mu divided by sigma. What's the y that we want to standardize? That's an observation of 60. The mean mu is 54, and the standard deviation, sigma, is 4.5. So we just fill in our numbers into the formula, and we compute that. And if you punch that in your calculator, you're going to get 1.33. So how do we interpret that? That means a herring of length 60 millimeters is 1.33 standard deviations above average. Alright, so notice that the original observation, 60, had the units of the original normal distribution, millimeters in this case. But the z-score doesn't get units. It's just interpreted as the number of standard deviations above or below the mean. Now we got a positive z-score, 1.33, so that meant that our observation was above average by 1.33 standard deviations. If you come out with a negative number, that just simply means that your observation is that many standard deviations below average. So now we're going to look at these next three examples. They go together, okay? And we're going to find the probability that a z random variable is between -1 and 1. So once again, as always, when we're computing these, we want to draw a picture. So our random variable is z. That's the special normal random variable that's centered at 0 and has a standard deviation of 1. And so we want to look at the area between -1 and +1 in the standard normal distribution. So we want to find this area. Now how do we find areas or probabilities associated with the normal distribution? We use the p-norm function. Now p-norm of 1, so the area to the left of 1, that's our number of interest, in the normal distribution that's centered at 0 with a standard deviation of 1, would give us the total area to the left of 1. But we only want to keep everything between -1 and 1. So we want to throw away the area to the left of negative 1. So we're going to do p norm of 1 minus p norm of negative 1. And when we punch that in R, we get .6827. And if we change it to a percent, that would be approximately 68%. Alright, so let's play the same game with the next example. The probability a z random variable is between negative 2 and positive 2. So once again, we'll draw a picture. It's a z random variable, which we know is centered at 0 and has a standard deviation of 1. That's the special normal distribution that's centered at 0 and has a standard deviation of 1. And we're tasked with finding the area between negative 2 and positive 2. So we'll play the same game. We'll compute the area to the left of positive 2 in the normal with a mean of 0 and a standard deviation of 1. And we'll subtract off the area to the left of negative 2 in the same distribution that's centered at 0 and has a standard deviation of 1. And when we punch that into R, we get .9545. Alright, and that would be approximately 95%. Alright, so let's play that game one more time and find the probability of z random variables between negative 3 and positive 3. So, once again, we'll draw our normal distribution, which is called z, and that means that it's centered at 0 and has a standard deviation of 1, and this time we want to look at the area between negative 3 and positive 3. And so we'll play the same game. This is going to be p norm of 3 minus p norm of negative 3 in the special standard normal that's centered at 0, has a standard deviation of 1. And when we punch that into R, we get .9973. Which is approximately 99.7%. So why did we do these three examples? Well, if you'll notice, we found that the area within one standard deviation of the mean is 68% approximately. The probability of being within 2 standard deviations is 95%, and the probability of being within 3 is 99.7%. And that is the empirical rule. Remember, we said the empirical rule worked for unimodal symmetric distributions, and we said that approximately 68% of observations from that distribution will be within 1 standard deviation, 95% within 2, and 99.7% within 3. Well, now I'm showing you that these areas actually came from the normal distribution. All right. Now a very important definition. The upper alpha critical point from the standard normal distribution, that is the normal distribution that's centered at 0, has a standard deviation of 1, is z sub alpha, this thing, such that the probability of being to the right of z sub alpha equals alpha. So what does that mean? We're going to draw a picture. It says in the standard normal distribution, z, which means we're centered at 0, with a standard deviation of 1, my z sub alpha is the place in the distribution such that what? The probability of being to the right of it, the probability of being bigger than z sub alpha equals alpha. So that means that this area is alpha. All right. Now, if there's alpha area above this critical point, how much is below it? Well, the whole thing has to equal 1, right? The total area under the normal distribution curve equals 1. So if there's alpha above z sub alpha, then there's 1 minus alpha below it. All right, so we're going to use this information to find our first z critical point, z sub 0.05. Now, when you see a random variable like z with a subscript, with a number between 0 and 1 in the subscript, that says, give me the z such that 0.05 is above it. So when you see this notation with your probability in the subscript, you're going to say to yourself, give me the z that has that amount of area to the right of it. Okay, so we're going to draw a picture again. Again, we're in the standard normal distribution, z, which is centered at 0 and has a standard deviation of 1. And we want the value in the standard normal distribution such that 0.05 is above it. So we want to find the value in the normal distribution such that 0.05 is above it. How are we going to find that out? Well, we have our p-norm function in R, and that is if we gave it a z, we can find the probability being to the left of the z, but we want to do the opposite, right? We're giving you an area, and we want you to come back with the value in the normal distribution. Well, we have a function for that called q-norm. However, q-norm thinks that you're giving it the area to the left of a value. Well, we can figure that out. Our z that we want has 0.05 above it. If it has 0.05 above it, how much does it have below it? Well, if it has 0.05 above it and the whole thing has to add to 1, then it has 0.95 below it. 5% above it, 95% below it. So we can use our q-norm function and tell it to give us the value in the normal distribution that has 95% below it in the normal distribution that has a mean of 0 and a standard deviation of 1. So we can go to R and give it our area to the left of the value, the mean of the distribution we're in, and the standard deviation of the distribution, and it'll give us that, 1.645. Now, when we got percentiles out before, we gave them units. This one, however, is the special distribution, the z, the standard normal distribution, which is just the standard deviations above or below the mean, so we don't have to give it units. All right, so that's important. You'll definitely be calculating some z-scores and some z-critical points in the near future. So now we get to the fourth order of business in the normal distribution, and that is, if I give you a data set and I want to know, does it look like that came from a normal distribution or not, how will we do that? Assessing normality. Many of our statistical procedures that we're going to be using rely on the fact of the assumption that it seems like the distribution is a normal distribution. So what would you do if I didn't teach you anything different? Up to this point, you just know how to create a stem plot or a histogram. But what if you only have just a couple points? It's not going to be easy to make a stem plot or a histogram. So we need something else. We're going to use what's called the QQ plot, or the normal probability plot. The QQ plot stands for quantile quantile. All right, a QQ plot plots the values of the normal scores against the data values themselves. Normal scores are just the expected values of the ordered observations in a sample, and different computer packages compute these expected values differently. So it says, okay, if this was from a normal distribution, where will we expect it to fall? It's easy to place the middle value, because we'd expect that to fall on the median. The rest of them require a little more thought, but we're going to let a computer package compute those for us. Now, if our observations are from a normal distribution, we would expect to see the points form a linear pattern on the QQ plot. So let's do an example. This example is heights in inches of 11 women. We've got a QQ plot here that we've created for you, and we want to try out determining whether it looks like these observations might have come from a normal distribution. All right, so what are we looking at? We've got a line drawn here on our QQ plot that kind of tells us where we would expect the observations to fall on the QQ plot if they were from a normal distribution. If there's a lot of deviation from the line, if they're making a shape, they're kind of following the leader off of the line, then we're going to suspect that it looks like they might not have come from a normal distribution. Now I see, and I know that you all see it too, that the points are kind of wavy. I see that. However, if you kind of squint your eyes for a second and look at it from far away, I don't see any definite shape being made. These points look fairly linear to me. So on this QQ plot, what I would say is I don't see a shape being formed. And that means the points are fairly linear. So I don't see glaring evidence against normality. That is, against the assumption that it looks like the observations came from a normal distribution. So again, you kind of want to stand far away, maybe squint your eyes. If you see basically a straight line, then you're going to see you don't see much evidence against the assumption that it looks like the observations came from a normal distribution. Okay. Let's take a look at another example of a QQ plot. So we've got this data set that is brain weights in grams for 62 mammals. And we made a QQ plot, and we'd like to check the assumption that these observations came from a normal distribution. Now when you stand back and you look at your QQ plot, you can just ignore the line that we've pre-drawn. It's very clear that the observations here are making what we call a U shape. Okay? They're definitely not linear. It would be okay here, but up here we're not doing so great. Definitely not linear. All right? So this QQ plot, or I see a U shape on the QQ plot. This is a clear violation of the normality assumption. These observations almost certainly did not come from a normal distribution. All right, what do we do if there's a violation of the normality assumption? In practice, we can try a transformation of the data. Some common transformations are taking a logarithm of the data, square root of the data, 1 over the data, etc. Okay? Now what we did to the brain weight data is we took the logarithm of the data. And now if we look at the normal quantiles against the log of brain weights, it definitely looks more linear. If I stand back and I kind of squint and make it blurry, I don't see any shape being formed. It looks fairly linear to me. So the QQ plot looks fairly linear. There's little to no evidence against normality. All right. Now I realize y'all are just starting out looking at QQ plots, so we need to give you a little guidance as to some common violations of the normality assumption that you're going to run across. So on your sheet of paper, we're going to have 4 rows of pictures and 2 columns. So if this was my whole page that we're looking at right here on the screen, leave enough room so that you divide your paper into quarters, and then we're going to draw some pictures on the left and some pictures on the right. All right, I just wanted you to be able to plan your space accordingly. Okay, so if I have a normal distribution, I have a QQ plot that looks like this. My data is making a U shape. Let's examine what distribution it looks like they came from. We already said, okay, it's not linear, so it looks like it's a violation of the normality assumption. But we can tell a little bit more than that. We can determine what kind of distribution they came from. All right, in the high end of the distribution, that is, in the high end of the values, if my points were from a normal distribution, they would be on the line, right? But our points are too high to be from a normal. So let's first draw our normal distribution. So if it was from a normal distribution, they would be on the line on the QQ plot. But our observations are too high to be from a normal distribution. They're above the line in the high end of the distribution. So that means that this right tail is extended out. All right. Now what happens in the low end of the observations on the QQ plot? Here are our points. On the low end of the distribution, on the low end of the observations, our points are again above the line. So instead of seeing histogram bars, remember this, we're going to picture this normal curve as a smooth relative frequency histogram. We've got normally, if it was from a normal distribution, observations right down there. But our QQ plot tells us that our observations are too high to have come from a normal. So this left tail kind of disappears. And ours starts about something like that. Now, the dotted line, what kind of distribution is that? That's a skewed right distribution. So a U-shaped distribution, a U shape on the QQ plot indicates a skewed right distribution. All right, let's try the opposite of that. Let's take a look at a QQ plot that's the upside down U shape. All right, so what happens when we have an upside down U shape? Well, let's first draw a corresponding normal distribution. If the points had fallen on the line, then it would look like that. But our points are not on the line. In the upside down U-shaped distribution, what are they doing at the high end of the distribution? They're below the line. So it takes away this right tail. In the QQ plot in the low end of the observations, again, we're below the line. My points are too low to have come from a normal. In the low end of the distribution, I've got observations that are more extreme to the left. So an upside down U shape indicates a left skewed distribution. All right, and now let's do two more. What happens if my QQ plot has an S shape? All right, remember, if they fell on the line, we can hopefully assume that they came from a unimodal symmetric distribution. But our points are in the upper end of the distribution are too low to have come from a normal distribution. They're below the line on the QQ plot. So that means we lose this right tail on the normal distribution, on our distribution. In the low end of the distribution, our observations are too high to have come from a normal. So we also lose the left tail. So our distribution loses its tails. So what we call this distribution is light-tailed. It lost its tails. And I bet you can guess the last picture we're going to look at and that is an inverted S shape. Alright, so let's try this one out. If the points were on the line on the QQ plot, they would have come from a normal distribution. Or if they were from a normal distribution, it should create a linear QQ plot. But our QQ plot is indicating at the high end of the values, they're too high to have come from a normal. So we're stretching that right tail out. In the low end of the distribution, our points are too low to have come from a normal. They're below the line. They're too low to have come from a normal distribution. So we're stretching the left tail out as well. So our distribution might look something like this. So when you have an inverted S shape, we have what we call a heavy-tailed distribution. More of your observations are in the tails. All right, now it's going to take some practice getting used to the QQ plots, but I would strongly encourage you to draw the shapes and try to think through it on your own, and we'll start the next class going over QQ plots.